In this video, we are going to look at the mean value theorem and some corollaries, some extensions of that theorem and ways we can apply this. The first thing we're going to do is talk about Rolle's theorem, which is stated here at the very top. Suppose that we have a function that's continuous on a closed interval. Looking at this picture over here on the right, the first picture, we're going between the points A and B. And we also are going to assume that we can take the derivative everywhere inside the interval A to B, not necessarily including the endpoints, but in the interior. If we know that the y values at A and B are equal to one another, f of A equals f of B, so we're saying these 2 points are equal, then there's at least one number in between them where the derivative equals 0. It seems sort of obvious looking at this picture that if we pass through a particular horizontal line twice, at some point the graph's got to turn around, and that turnaround point is where we have the tangent line leveling off to 0. So in this second picture, we're just making a distinction that it doesn't have to be only one individual place where the derivative equals 0. We've been calling that like a local maximum or a local min. It can happen in multiple locations, but we still have this horizontal line where f of A and f of B are equal. In this second example, we're showing that we've got these horizontal tangents in multiple locations. So let's prove this theorem. So f is continuous. That's one of the assumptions that we have. And we talked about last week that that means that it has an absolute max and an absolute min somewhere on this closed interval. So it has an absolute max and min somewhere on A, B, and it could be at the endpoints, right? We know that these max points occur in a couple of different locations. One is somewhere in the interior. And we knew that those interior points happen when the derivative is equal to 0. It could be also at an interior point where the derivative is undefined. And then the third option, like I said, would be at the endpoints. We're assuming that the derivative can be taken everywhere in the interior point. That was one of the assumptions. We're assuming that this function is differentiable everywhere inside. So we're going to actually reject this option. We're not even considering functions that the derivative is undefined. So option 2 gets ruled out immediately. Let's look at option 1. For option 1, if the max or the min occurs at some point, let's say C, let's say that, suppose that the max or min occurs at some point C, with C being in between A and B, then we know that the derivative of that point is equal to 0. We had a theorem before, right, that if we have a local max or a local min in the interior, then the derivative is equal to 0. So in that case, we know we've got that horizontal tangent. So in this case, we would be done. This is kind of just an extension of what we did last week. Option three was that the max min is at one of the endpoints. The reason I'm saying occurs at both of the endpoints is because one of our assumptions is that those two endpoints, A and B, are actually have equal y values. So if the max or the min occurs at one of them, it has to also occur at the other one, right? So let's say that there's a maximum point at f of A. Well, that's also equal to f of B. So that means that this has to be a constant line, right? Because anything in between them is going to be this horizontal line. These are the max points. If I have a graph like this, and I say this is the maximum point and this is also the maximum point, then everything has to be directly between these. So then in that case, our function, f of x, is going to be the same as f of a, whatever that value is, same as f of b, or a constant. And we know from taking derivatives in the past that the derivative of a constant function is going to be 0. So in that case, we've also proven it. Here's some examples where Rolle's theorem actually doesn't apply. And these have to do with one of the hypotheses that we have not being true. So one of the hypotheses is that we have the function being continuous on the closed interval. In pictures A and B, we've got discontinuity, right? And so they will both be examples where there's not necessarily a horizontal tangent, and that's because of these jump discontinuities that are showing up here. And then the third picture is breaking the hypothesis that the function is differentiable everywhere. When we've got a point that's a cusp like this, we can't take the derivative there. And in this particular case, there isn't a horizontal tangent. Just as a reminder, we said that for cusps, we can have a number of different tangent lines that cross through or intersect that point in exactly one place. So that's why it's not differentiable. So these are examples where Rolle's theorem doesn't apply. We can use Rolle's theorem to show that this particular function equation has exactly one real solution. We know that because the highest degree is 3, we should have 3 total solutions, but we want to show that there's only one that's real, and so then we would assume that the other 2 are complex. You can see a picture here, and if we were to graph this in decimals, we could easily see that it's crossing the x-axis once, but we want to mathematically show that this is true. I'm going to pick a point on the left here. Let's take -1. And if I plug -1 into the original function, let's see, I'm going to get -1 minus 3 plus 1. So we get -3 as the output. And then I'll take another point on the right. Let's take 0. And if I plug 0 in there, I'm going to get 0 plus 1. So the output is 1. And so, but the intermediate value theorem tells us that if you've got, these two y values, one below the x-axis and one above, that the function, because it's continuous, has to pass through the x-axis at some point. We know that this function is continuous because it's a polynomial, and all polynomial functions are continuous. So by the intermediate value theorem, we know that f of x equals 0 somewhere on the interval -1 to 0. Those are the two x values that we chose. If there were 2 points, A and B, where, let's say, the function was equal to 0. We're not going to do this kind of by contradiction. Suppose there were 2 points, A and B, such that f of A is equal to 0 and f of B is equal to 0. We're trying to show that there's only one place where the function crosses the x-axis, but I'm just saying, let's suppose that there's 2. By Rolle's theorem, then, tells us that there is some point in between those two, somewhere in this interval, A to B, C being an element of this interval, such that the derivative of that point, f prime of C, is equal to 0. Well, looking at our original function, the derivative is 3x squared plus 3. Just going back up here and taking the derivative, 3x squared plus 3. And this is always greater than 0. So we can't have this. There's nowhere that the derivative is equal to 0. So that's a contradiction of our assumption. There can't be 2 different points where the function takes on the value of 0. So in that case, we can make the conclusion that f has no more than 1, 0. All right. So now we're to the point where we are going to talk about the mean value theorem, which is the main theorem for this particular section. We are going to assume that we have a function that's continuous and differentiable. Again, it's continuous everywhere on the closed interval, differentiable everywhere in the interior. We don't have to worry about the endpoints. What this is saying is that there's at least one point somewhere between A and B where the derivative at that particular point is equal to the slope of the secant line. So if I look at the 2 endpoints here, A and B, and I plug them into the function and draw this secant line between them, and I get this particular slope. This theorem is saying that there's some point in between there, it happens to be C here, where the slope of the tangent line is parallel to the slope of that secant line. These pictures down here are what we're going to be using for the proof. So we'll just leave those there for a second. So for our proof, let's start by looking at picture number 1. The secant line that we're looking at is between the 2 points A and B. Those are the x values. And so then the points are A, comma, f of A, and B, comma, f of B, right? And let's call the equation of the secant line, let's call that a new function. Let's call it g of x. So let's let g of x be the secant. Can we get an equation for that? Well, let's see. If we think about the point slope equation, we can get an equation of, let's see, y minus y1. So I'm going to take g of x minus f of a, the y value of my first point. So I took y, or g of x, minus this guy here. And then that's going to be equal to the slope in between them, right? So this is y minus y1, m The slope between those 2 points is going to be f of b minus f of a over b minus a. Again, taking these 2 coordinates. And then I multiply that by x minus x1, again, going back to the first point, which is going to be a. So this is the again, m times x minus x1. So this is just a different version of the point slope formula. Okay, so let's rearrange this. I'm going to move the f of a onto the left-hand side. Plus f of b minus f of a, b minus a, x minus a. Okay, I just move the f of a over onto the right-hand side. And then what I'm going to do, actually, I'm going to distribute this number to both of these items here. Because I eventually want to take the derivative and I want to have these be separated. And that's times a. Okay. This should be minus, right? Let me just double check that. Okay. If we look at picture number 2, let's go back up here. We have this, we're thinking about the distance between any point between these 2 graphs, and we're calling it a new function, h of x. So h of x is the function f minus the function g, and we've just drawn that down here. And we can see that these 2 points are 0. That's because if I look at both f and g, they intersect at the exact same point, so the distance between them is 0 there. Okay. So let's let h of x equal f of x minus g of x. And then what I'm going to do is take what I have for g of x up here and substitute that in. Let's see, when I subtract this though, I'm subtracting this. So that changes to negative, that changes to negative with this last term. Looking down here, actually, let's go here. I'm subtracting this whole thing. So this first term will change to negative, this term will change to negative, but that last term is going to change to positive, right? It's actually not going to matter. Oops, I forgot an x here. Okay. Now we know that this new function h is continuous because it's a combination of f and g that are both continuous. And so, and we also know that we can take the derivative because it's a combination of f and g, which are both differentiable, then h is also differentiable. I state that just because that means that it meets the criteria that we need for Rolle's theorem, so we can apply Rolle's theorem. The 2 endpoints we just saw, h of a and h of b, are equal to each other. So we know that somewhere there is a point C in the middle. So there is C somewhere on that interval such that h prime of that number is equal to 0. Looking at the picture again up here, we're saying the two endpoints are equal to one another and they're at 0. So there has to be a horizontal tangent somewhere here where the derivative is equal to 0. So now what we're going to do is take the derivative of this function h that we just found. This is where we got a bunch of algebra. Let me make some more room here. All right, the first thing I want you to look at is that we have some things that are just numbers, right? Anything where I have an x, that's a function, but anywhere that I have a or b plugged in, that's just a number. So this is just a number right here. So when I take its derivative, it goes to 0. Similarly, this is just a number. So when I take its derivative, it's also going to go to 0. So let's see, h prime of x is equal to, right here, we'll have f prime of x. Right here, we'll have 0. Here, we've got some number multiplied by x. So when I take the derivative of a constant multiplied by x, I just get the constant. Even though it looks complicated, it's just a number. And then that last term is also going to have a derivative of 0. So the derivative of h ends up simplifying quite nicely. Now let's evaluate it at the point c. H prime of c, plugging c in for all of our x's, and we know that this has to equal 0. So then we can say that f prime of c equals f of b minus f of a over b minus a, which proves that the derivative somewhere at that point in the interval is equal to the slope of the secant line. Here is an example problem. This example is fairly simplistic because a lot of times it's, even though we know that there's a point where the slope of the tangent line is parallel to the secant of the two endpoints, sometimes it's difficult to find. So this example is kind of easy just to show you the concept. We know that x squared is a continuous function and it's differentiable between 0 and 2. What are the endpoints? If I plug them into the function, let's see, f of 0 would just be 0 and f of 2 is 4. So I'm thinking about those 2 points, 0, 0, and 2, 4 as the endpoints. I can see them here in the graph. The slope between those 2 points is going to be 4 minus 0, 2. It's going to be just 2, right? When we look at the original function, the derivative of the original function is 2x. And so the mean value says that there is some point c between 0 and 0 and 2, such that the derivative at that point is equal to 2, this, the slope of the secant line. So if I look at what the derivative is at c, that would be 2 times c is equal to 2. So c is equal to 1. So what it's telling us is that the point where the tangent line is going to have a slope that's parallel to this one is at x equals 1. Seems pretty easy when you look at the picture, but it's not always easy, again, to find that particular point in between the two endpoints that we're talking about. If we think about the secant line as the average rate of change, let's say that this is the average rate of change over a particular set of time, let's say 0 to 2 seconds or something. What this is saying is that at a particular point, right at 1 second, the instantaneous rate of change is exactly equal to the average rate of change. So a practical example would be, and I'm going to make a little space here. Suppose that I have a car that's accelerating from 0 miles per hour, or from 0 to, let's say, 352 feet in 8 seconds. So then the average velocity is going to be 352 feet in 8 seconds, which ends up being 44 feet per second. So in between that 0 to 8 second time period, somewhere the speedometer is going to read exactly 30 miles per hour. Somewhere between 0 and 8 seconds. Just instantaneously, this 44 feet per second, I'll leave this for you guys to do. 44 feet per second, if you change all of the units, will end up being 30 miles per hour. But it's saying that at some point there's an instantaneous point where the speedometer will say exactly 30 miles per hour. It's just going to be for a second, and it's going to equal to the average acceleration over this time period. All right, I'm going to stop here and then start a new video.